Our second plenary session for today, and for me it's a great pleasure to introduce the speaker, Professor Javier Garcia Martinez from the University of Alicante, Spain. He is a professor of inorganic chemistry and director of the Molecular Nanotechnology Lab at the University of Alicante in Spain. He is recognized as a leader in nanotechnology and material science. He is co-founder and chief scientist of Rife Technology Incorporated in Boston, Massachusetts. This is a spin-off funded, MIT spin-off for commercialization hierarchical zeolites for diffusion limited applications. Rife's proprietary technology improves traditional zeolite catalysts and adsorbents through the introduction of the broad channels or molecular highways which overcome the diffusion limits of these materials, leading to better yields, process efficiency, and process economics. He has published extensively in the areas of nanomaterials and energy, and he is the author of more than 25 patents. His latest books are The Chemical Element Valley, Chemistry Education, and Mesoporous Zeolites. In 2005, Javier was awarded the Europe Medal, awarded annually to the outstanding European chemist under the age of 35. And he received the Silver Medal of the European Young Chemist Award in 2006. In 2007, Javier received the award from MIT Technology Review magazine. Since 2010, he is the member of the Council on Emerging Technologies of the World Economic Forum, which recognized him as a young global leader. Javier is a fellow of the Royal Society of Chemistry, member of the Global Young Academy, and bureau member of the International Union for Pure and Applied Chemistry. Please.
Okay, thank you. Thank you for the kind presentation, and thank you also for the kind invitation. I'm delighted to be here today to tell you about my work and some of the people's work to contribute to the Sustainable Development Goals. The first thing I want to say is congratulations to our Russian colleagues. I know how meaningful this conference is for all of you. We are all celebrating the 100 years anniversary of the periodic table, and this guy and his dream of organizing the elements in a way which is so inspiring and useful has become an icon of science and is going to be the leitmotif, the main driver of my presentation. So once again, happy anniversary to our Russian colleagues. I'm delighted to be here today. One of my dreams, this is not Mendeleev's dream, now this is my own dream, is to transform the periodic table in a roadmap to achieve the Sustainable Development Goals. And this is a periodic table I made to convey that message. How we can organize chemistry around these very inspiring goals. And I'm going to be talking about how we can achieve those and how chemistry is key to achieve these goals. We can provide solutions for food, for energy, for the environment. And we can do that in a way that is going to contribute to fight climate change and some of the other main problems we have today. And in order to do that, we need to use 4 main connected areas, which are create, conserve, connect, and care. And the chemical industry knows how to do this very well in a way that we produce our materials in a more sustainable way when we are considering the whole cycle analysis of the production. So with that in mind, it's very useful to look at this report. I don't know if any of you have read this report, but it's very inspiring because here, United Nations summarize the main achievements of our previous goals, the Millennium Development Goals. And we can feel very proud of the progress we made and especially of how science make big contribution to achieve these Millennium Sustainable Goals. Like, and I think that's very telling, now instead of having more than 12 million children dying after the age of 5, now there is only 6. Now, instead of 2.3 billion people having clean water, there are more than 4 billion people with access to clean water. And I think which is quite dramatic is that almost 100% of all the ocean-depleting substances has been eliminated since 1990. And all of this has been because the chemistry community has been provided with solutions, and actually those solutions have been implemented. So we have a solid ground to build the next sustainable development goals. So my talk is going to be about simple solutions like providing magnesium sulfate to a pregnant woman that significantly reduce the mortality during birth because reduced blooding, and also to incorporate beta-carotenes into rice, the golden rice, who reduce the problems in South Asia of people that don't have enough vitamins in the diet. So I have time to talk only about 4 of these goals. I'm going to be talking about how we can fight hunger, how we can provide clean energy to the planet, how to fight against climate change, and a little bit about one of the goals which is usually not very prominent, is how to create partnerships, how we can work together towards achieving these goals. First, hunger. Here we can feel very proud because the chemistry community has a big role in the Green Revolution. A reaction that seems very simple on paper, which is just reacting nitrogen with hydrogen, has been the key for providing food to so many people. This reaction is in fact extremely difficult, as you know, from a thermodynamic point of view. The triple bond in the nitrogen molecule is very stable. The activation energy for this reaction to happen is extremely high. Through the use of catalyst, I'm going to be talking about catalyst during my presentation, we can make this reaction happen and provide nitrogen that afterwards can be transformed into fertilizers. This seems, again, a very simple reaction, but it's very meaningful. This is one of the plots that should be in every chemistry book. We should be feeling very proud about this plot. If you have not seen it, let me go with you through this plot because it's extremely important. It was published in Nature Geosciences a few years ago. Since the discovery of the Haber-Bosch process, the population of the world has exploded from less than 2 billion people to more than 7 billion people. Some estimations suggest that without the Haber-Bosch process, now we will have only a population of 3.5 billion people. So in a way, artificial fertilizers are providing food for half of the planet. If somebody asks you which are one of the main contributions of chemistry to society, I think the Haber-Bosch process is a very meaningful contribution because it's providing food to half of the planet. Actually, a significant part of the nitrogen in our bodies is coming from a chemical plant. A plant like this one here, a huge plant. And that's one of our challenges. The Haber-Bosch process takes between 1% and 2% of all the world's energy production. The first thing you need to do to produce ammonia is to actually generate hydrogen. There is no free hydrogen in nature. You need to produce it. And it's usually produced through reforming of methane. Well, this is a very pollutant process that involves the generation of large amounts of CO2. But even if we will have enough hydrogen to produce ammonia, this part over here, which is the reactor that actually produces the ammonia, carry out that reaction, operates at extremely high conditions, not so much in terms of temperature, but at very elevated pressures. And as we know, nature does the same thing at much milder conditions. And nature doesn't need hydrogen. It just needs protons. So when we look at this enzyme, nitrogenase, we realize that the catalysis is happening in this cofactor when you have this iron cluster cofactor where the magic happens. There are several iron atoms, and the D-nitrogen molecule can bind to one or several of these iron bonds, and through a very mild, you see activation energies are quite low process, you can carry out this reaction again under very mild conditions. In the last 30 years or so, inorganic chemists has worked very hard to mimic this process, and one of the main breakthroughs in the field, actually now quite old, is this chat cycle, when with the use of molybdenum and tungsten complexes with this phosphine, you can fixate actually 2 molecules of ammonia per molecule of D-nitrogen, again, without the use of hydrogen. More recently, this has been a main breakthrough just a few years ago, this mononuclear iron complex is able to do the same at higher efficiency, imitating the cluster, as I said before, involves iron. There is something magic about iron and the Haber-Bosch process. Both the heterogeneous and the homogeneous catalysts contain high amounts of iron. But probably the most striking piece of research in fixation of nitrogen is probably this paper, which is actually quite amazing. By reacting nitrogen with water, nitrogen with just plain water, under very mild conditions, for example, at 25 degrees C, using only 1.2 volts, you can obtain ammonia at a 35% yield. That's an amazing yield, much higher than either plants or the Haber-Bosch process. And it's very beautiful because actually you don't need to use pure hydrogen. You can use just air. Air plus water, with a little bit of electricity, actually a pretty low voltage, you can get ammonia 35% yield. This piece of research is indeed very inspiring. But we can do much better now in terms of energy. And I have some good news to share with you. We have reached grid parity in most part of the world. So, in all of these big economies, producing electricity through solar panels or the solar technologies is actually cheaper than producing energy by any other means. So this is actually very good news, and the source is not very suspicious. It's a Deutsche Bank, so not a very scientific organization. So they say this, I actually kind of believe it. And this is 2015, as the technologies keep increasing, or improving, now we have better yields. This is another of these plots that should be, in my opinion, in every chemistry textbook. It looks very complicated. It's extremely simple. What this plot is showing you is the different technologies, solar cell technologies, to produce electricity from solar light versus time, and see the kind of improvement we have obtained in the last 40, 50 years. And this increase is not linear. There are steps. Those steps are breakthroughs that usually happen in universities, like the ones that I'm highlighting here, or maybe national labs, fundamental research. And now that we are advocating for International Year of Basic Science, this kind of plot is very useful. Main breakthroughs happen in universities or national labs. And now when you get efficiencies which are high enough, now companies like these spin-offs are taking those breakthroughs into the market. I do believe that those entrepreneurs that will take scientific discoveries to the market are going to be the most important agents of transformation for this century. Nobody knows which energy technology is going to win. Most likely it's going to be a mix, and it's going to be depending on your location. What kind of resources do you have? But we know that chemistry will play a major role in producing energy more efficiently. We will need the periodic table. We will need the elements in the periodic table to produce this energy. And as we were hearing in this morning lecture, we should be using elements which are abundant. We cannot use the whole periodic table. Of course, we cannot use the super heavy elements. We cannot use the scarce elements. We need to use earth-abundant elements. And there are very few of them. But I have, again, good news for you. The periodic table used to be a two-dimensional chart. Nanotechnology is adding a third dimension to the periodic table. What do I mean by that? When Mendeleev was organizing the elements, he was thinking of individual set of properties for each element. When he was thinking of carbon, he had coal in mind, maybe graphite. And he was organizing the elements based on the properties on one particular allotrope of carbon. But now we have many allotropes. So indeed, nanotechnology is adding a 3 dimensions because it's not only the atomic number who is defining the properties of the element, but also what kind of a structure you are introducing in that element. And I have, again, good news for you. Just last month, there was the report of a new allotrope of carbon, a beautiful structure. That structure, the cyclo-18 carbon, doesn't have any hydrogen atoms. It's a pure carbon molecular allotrope of carbon. The other ones, even graphite or diamond, will have some hydrogens in the surface of the crystal. This one is a purely carbon molecule, which is a new carbon allotrope, which is actually a molecule. So every day, we are increasing the different tools that we have from the periodic table, going from the 2-dimensional table that we all study to this new 3-dimensional table that nanotechnology is introducing. Again, this morning there was a fantastic presentation on batteries. I'm not going to say too much, first of all, because it's not my field of expertise, but I really want to introduce a few examples just to show how by using nanotechnology, to use nanostructure electrodes like this templated nickel electrode for the production of batteries, you can have extremely high charge and discharge batteries like this one that charge and discharge in just 1 minute. But this one is based on nickel. What if now you use a more abundant elements to produce your anodes, like this battery that uses aluminum, and it has a very high power and energy density, where it's extremely lasting. As you can see, it can last for many cycles, over 3,000 cycles, using just aluminum and graphite. So there is a lot of hopes for using alternatives, not just of lithium, but also when we are thinking of other elements like the one I'm mentioning here. But if there is one process which is very inspiring, it's definitely photosynthesis, converting CO2 into fuels. Plants convert CO2 into carbohydrates. Those are our fuels. But CO2 these days can also be transformed into other kinds of fuels, fuels that can actually replace fossil fuels. And again, one of the most inspiring pieces of research of the last few years has been the artificial leaf, which is quite amazing. You can see in this little video here how this system that contains a photocatalyst can split water into hydrogen and oxygen with no wires, just by exposing the catalyst, the photocatalyst, to solar light. It's just unbelievable. Another advance in the field has been the production of black titania and black semiconductors that can absorb the spectrum of visible light in a more efficient way. Based on this technology, my research group have developed these new dye-synthesized solar cells where the metal complex, the ruthenium dye, is incorporated into the structure of anatase by using salt gel chemistry. By doing that, we have achieved the highest efficiency of any low-temperature solar cell with almost a 9% efficiency, and now we are working towards getting a 10% efficiency using this very simple chemistry to produce solar cells. The other piece of information, the other sustainable development goal I want to talk about is how to fight climate change. I'm going to be a little bit bolder, and I'm going to be talking about a sector that is usually not present in our conferences, but which is extremely important, the refinery. This is one of the main chemical processes and is responsible of a huge amount of CO2. If we can do anything to improve the catalyst use here, we can do a lot to fight climate change. This is the catalytic cracking unit. You have the regenerator, the catalytic cracking reactor, and the fractionator. The catalyst, based on a zeolite, is fed into the reactor, and the vacuum gas oil is exposed to the catalyst. In a very short period of time, at high temperature, the hydrocarbons are cracked into valuable products, and the vapor are collected, and then they move to the fractionator, when you can separate the different fractions, and you can have your gasoline, your diesel, your olefins. This is how our fuels and olefins are produced around the world. It's a major process. But it produces a lot of CO2 because this catalyst deactivates very quickly, is full of coke, and then this coke, this carbon, needs to be burned out to regenerate the catalyst, and a huge amount of CO2 is produced just by this regeneration process, where the zeolite is reactivated to be used again. So a few years ago, as it was said before, I founded Rive Technology to incorporate nanotechnology to make this process more efficient. And I will try to explain to you what's the basis of our technology. The catalytic cracking catalyst is based on the use of zeolites. Zeolites are aluminum silicates. They have this porous structure, very crystalline porous structure that repeats over the 3D space. And these pores are actually extremely useful because hydrocarbons can go through these micropores. They can get inside. Inside these catalysts, you find the active sites, and then the hydrocarbons traveling through the micropores of the zeolite can reach the acid sites and be cracked into more valuable products like gasoline, diesel, and olefins. This is the actual catalyst, how it works today. But there is a main problem. We are all aware of what's the problem. In heavy crude oil, we have bulky hydrocarbons that cannot get inside the porosity of the zeolite, and then is not converted, and actually you produce coke, and that coke generates CO2. We have found a way to incorporate larger porosity, mesoporosity, in the order of 4 to 5 nanometers, that now can be used as molecular highways to allow for the access of even the larger hydrocarbons. So these hydrocarbons that otherwise will produce CO2 can get inside your catalyst and can be cracked 1, 2, 3, 4 times to produce that gasoline, diesel, and olefins without producing so much coke. This is not science fiction. This is actually a technology that is being used in refineries through all the world. We sold this company just a few months ago to Grace, and I'm glad to be able to present to you some recent data from the major refinery in the US, from Motiva in Texas. So as you can see here, based on our predictions, but also in actual data, we can decrease the amount of CO2 produced, the amount of coke produced in the FCC unit by 10%, which is very significant. At the same time, we are increasing the production of the liquid fuels like gasoline and diesel and reducing the formation of hydrogen in coke. This creates value for the refiner, so it's money that goes between $10 and $50 million per year per refinery, but also less CO2 to the environment. And that's why I want to introduce this example, because with better technology, you can create both value to the industry, so it's going to be commercialized, so it's going to be accepted by the industry, and at the same time, you can create benefit for the planet, which is a very significant reduction in CO2 production. So at a constant refinery through output, maintaining the same amount of gasoline, diesel, and olefins that you are producing, we reduce for this particular refinery a 14% in the amount of CO2 which is produced. And that means thousands of tons of CO2 per year. So my final message is that while we are working for the batteries of the future, the solar cells of the future, the whatever technologies we want to use in the future, we need technologies today to reduce the footprint of the technologies we are going to be using for the next 5, 10 years, because refineries are going to be used for many years to come. So we better use more efficient catalysts that produce less CO2. And as I said, just to end, the last sustainable development goal I want to talk about, which is partnerships. And here is when I want to bring IUPAC. And why IUPAC is important in achieving these goals. First of all, because we need a common language, both in industry and academia, to share knowledge. I don't speak Russian, that is quite obvious. My English is so-so, but you saw the molecules on my presentation, and I didn't need to translate a word, because there is a common language for chemistry. You recognize the molecules and their reactions because we have a standard way to represent and to speak everything chemistry. And we get this for granted, but 100 years ago, this was a major issue, and the main scientists and industry leaders of the time realized that issue, and that was the main reason to create IUPAC, to create a common language of chemistry, something we get for granted, but it was a major, major undertaking for many years for IUPAC. What's the next challenge for IUPAC? Is not only create a chemistry language for humans, but actually also now for machines. You know how much information goes into the digital world, through papers, through tables, everything. So just imagine if now we will have a language that could be understood by machines. And that is what IUPAC is doing with the INCHI Trust to create this INCHI name for every single molecule, where you have information about the composition, the connectivity, and the geometry of the molecule in a way that machines can recognize that molecule, and by doing that, using machine learning and big data analysis to recognize the trends that otherwise we couldn't recognize. So there is so much information that even in your own field, you cannot read all the papers. But imagine if you have a machine that is helping you to recognize big trends in chemistry. And there are already some examples, both in material science and chemistry synthesis, where through the use of machine learning, we have clues of where to go or where to explore in the future. We are, of course, also celebrating our 100 years. 2019 is very special, of course, because we are celebrating the 100 years anniversary of the periodic table, the International Year of the Periodic Table, but also the 100 years of IUPAC. And we have been doing a lot this year. I just want to bring you 3 examples of what we have been doing. The Global Women Breakfast on February 12th has been a magnificent way to celebrate women in science, but also to allow women and men to get together for breakfast and discuss everything related not only with women in science, but diversity in general. The other effort has been this periodic table challenge, an online quiz where more than 100,000 students have participated from more than 120 countries. So there is a lot of interest in the periodic table, and through this online quiz, we have been able to reach a very large audience, actually all over the world, in a very low cost. And also we are recognizing both young people, like with this periodic table of younger chemists, when we recognize young chemists that are doing amazing things, not only in research, but also promoting science in the local communities. So we have identified 118 chemistry leaders of tomorrow and awarding them with a chemical element. Imagine if IUPAC will recognize you with your favorite element. I mean, that's quite of a recognition. Of course, only Oganessian can have a name after him, but you know, this is a nice way to recognize also young people with a chemical element. And every 2 years we recognize the best women in chemistry and chemistry engineering as a way, again, to recognize diversity. We at IUPAC are extremely committed to promote diversity. This has been a main driver for my research. A few years ago, IUPAC asked me to write this editorial for Chemistry International about how chemistry can help to achieve the Sustainable Development Goals, and this article was the foundation for a recent book which actually has the same name of my presentation, The Chemistry Element, which I think compiles different technologies that give us hope in achieving the Sustainable Development Goals on time. With that, and this is just more an invitation for the younger people in the audience than anything else, we have this tool. We have a fantastic tool today, and it's only creativity that what we need to shuffle the periodic table, to use the chemical elements in a creative way, to make the periodic table your own tool and use it every day to create solutions for the future. Thank you very much.